Just waiting. I'm going to just type them in. So I don't really... It's all just a number answer. You can do them in your head maybe, yeah? Right. Open. Wait, why are you so late? Saw a picture of you in a magazine recently. I'm going to give you a hard time about that, you know that, don't you? Sit down. Have you seen this picture? Yeah. Pretty kind of stupid looking, huh?
I was wearing a cap.
What?
I was wearing a cap. You have something on your shirt.
Put yourself together, Joshua.
What you told moving for you, that?
What?
What you told moving for you, that?
Yeah, now you see. No, it's the problem with me drawing comparisons like that. Okay, here Joshua, make yourself useful and give me the worksheet from yesterday. Right, so let's go through these. The first one. Did I do the first one in class?
No.
No? Okay.
Is it number 3?
Right, okay. Let's have a look. Oh, come on. Here we go. So the first one here, I'll just type the answers up on the screen. No, I'll put them in the answer box. Come on, you can do it. Get them there.
Your laptop is not enough powerful for it.
No, it's because of stupid Windows. Right, so the first one, what's missing in the formula? X 23992. X, which is on the top and which is on the bottom? On the bottom is 92 and up the top is 239, yeah? Okay, the next one, what's missing? What's missing? 62 and 29. You know what, I'll just write the two numbers in. 62 and 29. Okay, the next one? And the next one? 56 and 27. Okay. Next?
27 and 12.
Oh. And then the next, let's see. No, it's not done. I'm on F. 23, 13, yeah? Wait, 2313? Yeah. And then the last one, 12.6. What's wrong, Tanish?
I have a problem with D.
D, okay, let's have a look at it. D is 5627. So if you look on the left, Tanish.
25.
Hang on, just listen, please. On the left, how many protons do you have? 26, yes?
Yeah.
And on the right, you only have one, so it should be 25. Oh, okay, that's wrong then. Who said 27?
I heard 25.
Yeah, okay, 25. Right, is there anything else?
No.
Is that okay?
Yes.
This is for the who did good. Just right here, okay, good.
Oh, for you.
The telephone question.
FYI, this is the homework you were supposed to do last night. That's why I'm doing it now. Well, good for you. Congratulations. Let me get you a medal. Right, 2. So what's missing in 2? X, 220 and 82, yeah? What did I forget? Oh no, I didn't forget, it's just on the next page. Yeah. So, next here, A. 220, yeah? No, sorry, 210 and 82. No. Yes.
Yes.
Yes. 210 and 82, okay. Next. What's next?
214.
214 for sure, yeah, now just be careful.
84.
Yes, very good, 84. Wait. No, not 80. Not 84.
Oh, it's 84.
Hang on.
84 minus 1 is
84, yeah, no, it is 84. Yeah, that's what we have, yeah. Okay, next one. 12, 5. And then the next one, now.
What?
The next one has has a process. So there's 2 answers. Well, there's two things missing. Please, Joshua, please. Do you need me to write this one out, or is it okay? You have the answer? So firstly, what goes with the uranium? It goes...
After the first arrow, it's 239, 93.
Yeah. I don't know if they want something after the first one. They're not being very clear. No, I guess not, sorry. After the first arrow is 239, 93. And then after the second arrow,
239,
239, 94. Okay. The next one, 98, 80. Okay. And then the next one, 63, 30. And then the next one, 32, 16. Okay. And finally number 3. Now number 3 gets a little bit tricky. I think we might want to just have our program open. So number 3, they're all going to be simultaneous equations because you don't know how many alphas and betas you have. So we'll say that we have X alphas and Y betas. What's wrong, Carl?
What?
Is everything okay with you today?
Why are you asking Mr. Steven?
You just seem unusually happy.
Maybe because yesterday I slept at 6 and woke up today at 8.
So you're full of energy?
Yes.
Great. Right, so number 3, we have X alphas and Y betas. So on the left, how many protons do we have? How many at the top? What's the top on the left? 2, 3, 2. So 2, 3, 2. And then on the right, what's the top?
208.
208 plus X.
X times 4.
Yeah, 4. An alpha has 4 on the top. And then what does the beta have on the top? 0. So plus 0 Y. And if I look at the bottoms, it's 90 equals 82 plus 2x minus 1y. We did this in the last class. So it's a simultaneous solve system 2. and it's line 1, line 2, so 6 alphas and 4 betas.
Do we only do this?
Yeah, this is how to do it.
No, like, we don't have to do it. Do we have to do the direct direct?
No, I'm just being lazy. 6 alpha, what did I say, 6 alphas and 4 beta. Okay. Now the next one, we just have to really change the numbers here, but it's the same deal. So instead of 232, it's 237, and instead of 208, it's 209. And then here, it's instead of 90, it's 93, and instead here it should be, what's that, 83, yeah? Okay. Solve system again 2, and then we have the first one and the second one, and we solve 7 alphas and 4 betas. Okay, halfway there. C. Two, 3, 8. And 206, and then the second one is 92 and 82. So solve system again 2. What did you get, Joshua? 8 alphas and 6 betas. Okay, and then D, let's see, 235, 235 and 207, and then here 92 and 82 as well, yeah? Solve system 2. Okay, so that last one's 7 alphas and 4 betas. Okay. Right, so I think for the exam, it's a really good question. Even the most difficult one here is not too difficult. It's just a simultaneous problem. So what we're going to look at next now is a bit more about radiation and the decay. And we're going to look at the rate of decay. So let me just open up my, I'll get up my pen. Of the what?
Isn't that
Well, firstly, decay is antonym of growth, so the opposite of growth. But for definition, decay is, do you want a verb or the noun? So decay as a verb means to reduce, to make less of, to lose its attributes and properties. For noun, decay, put Dr. Pepper away, please. We don't really use it as so much as a noun in physics, but decay, you know, would be to describe after the verb something as decay. Yeah, so you'd say, oh, look at that decay, you know, like on a tooth decay, you know. Usually means it's in a bad state. Yeah, we can use it like a lot of verbs and nouns. They can be used both as a verb or noun. So decay is one of them. Okay, so we're looking at radioactive decay. So we know from the last class that radiation is the falling apart of an atom. The alpha, beta, and gamma radiation is actually the atom falling apart. So with alpha, what is released from the atom? Helium, yeah. with beta electrons, and gamma is an electromagnetic wave. Different isotopes will decay at different speeds. So we're going to look at radioactive decay rate. How quickly the atom decays. So let me just open up my writing program here. Close for the moment. And in fact, we did a little bit of this in math semester 1 with the practical problems on exponential and logs. One of the questions was a decay question, and actually also in the ODEs as well, the rate of decay. So you actually have seen the formula already. Parts of it are. I don't. It's in the formula book, but I don't think all the ones are there. Like the formula for half-life's in there. Okay, radioactive decay. So we'll use our reliable friend uranium-238. And uranium-238 is falling apart, so it's emitting alpha, beta, gamma radiation. So let's say, for example,
what group is it? Uranium
isn't it in that weird last line group, isn't it? Yeah. I don't have the periodic table. Isn't it? It's yeah, it's in the weird row. Yeah. Okay, so we'll take uranium 238 will eject alpha, beta, and gamma radiation, or well, just eject alpha, beta, gamma radiation, or particles if you want, although gamma is not a particle really. Okay, but it won't continue to do this forever. No, it will, and it won't continue to do it at the same speed. So as you can imagine, at the beginning, there's lots coming out, and over time, there's less coming out. So, at t equals 0, the U238 will release the most alpha, beta, gamma. And as time increases, this will reduce.
So it's constantly radioactive.
Yeah, it's constantly emitting alpha, beta, gamma, but it just reduces the amount over time. So if we were to look at a graph, I'll show you the graph now. Yep.
As the time increases, the radioactive decay reduces.
Yeah. Well, we have to be careful with our language. The rate of decay decreases.
Well, what's the difference?
I thought it would increase.
No. So what I'm saying is, as time goes by, if you could measure how much alpha, beta, gamma was coming out, there'd be less and less after each second. Okay. The best way, one way to think about this is if you fill a bucket full of water and put a hole in the bottom. At the beginning, this is when the water is coming out the fastest. But then as time goes on, and as it gets smaller and smaller, as more and more comes out, it doesn't come out as fast.
But that is because pressure.
Yeah, but it's called an analogy. I'm just.
We're not making the hole in uranium.
I'm just.
But, I mean, what you mean?
I'm just trying to give you a simple comparison. I'm not saying there's a... never mind.
Well, I'm asking,
yes.
when something is decaying, let's get in mind.
Yeah.
Is uranium getting bad as the time?
Yeah, the uranium isotope is getting smaller. It's falling apart.
So increasing decay.
So you're using decay to describe as how much is being...
Yeah.
Well, we don't usually use the language that way around, but you're right, it's more and more decayed as time goes on. But it doesn't decay as fast as at the beginning, yes. Yeah. But no, if you put it that way around, yeah, you can say that. Anyway, as time increase, this will reduce. So if we draw a graph here, can I go to the graph? Yeah. So what do we put on the x-axis? Well, that'll be time in seconds. And what about on the y-axis? Well, what unit should we put, do you think?
Speed.
The number of hours.
Yeah, it needs to be some kind of count. So what we'll do is we'll put n. No, well, math actually is acceptable, but math is fine, but usually we put n, the number of uranium isotopes. So maybe at the beginning you have 10 to the 10 uranium isotopes. And then over time the uranium will decay and there won't be any uranium left because it's throwing away protons and neutrons. So if we were to look at the graph, here is N0. As time goes on, the amount of uranium that's remaining is decreasing. Exponentially so, yeah. No, it doesn't. Yeah. Now, I think Joshua or someone else said, could you put mass on the y-axis? You could get, because of course mass of each uranium isotope 238 is the same. So you'll get the same graph, just a different unit on the y-axis. So that's acceptable, but not normally done. And so yes, it's exponentially decaying. So you can actually have a formula here, and the formula is n equals n0 e to what power?
Minus E.
There'll be a minus t in the top for sure, yeah? And some constant. But a plus or a minus? Yeah, it'll be minus k t.
Is K time constant?
No, it's different for each isotope. What? I'm sorry, what can I say? Deal with it. Question? Sorry, sensible question? No? Okay. Now, we have some further terms we can talk about. So there's this idea known as half-life.
When it loses the alpha number.
Yeah. It is the time taken to go from the initial amount of isotopes to half the amount.
So half-life is time.
Half-life unit is time. So if you look here on my graph, this is called the half-life time. The time until you have half initially of what you had initially. So I'll write that definition down. The time taken to lose half the number of radioactive isotopes. Okay. I wonder what I think I'll look it up what the half-life is anyway. But the reason half-life is convenient because you get a very clear picture in your head of what half-life means. it's the time taken for half to be gone. And in fact, you can use that not just in radiation, but a lot of things. So for example, how many students did we have in this course at the start? 10. And how many do we have now?
7.
Right, wow, how many students right now? Yeah. 7, isn't it? Yeah, but he's still in the class, so 8.
9.
Mohammed, 9.
Mohammed.
He's not. Yeah.
What?
Yeah. So 8.
Mr. Student again?
Hey, what can I say? Looking at you, Joshua. So there's 8. So we lost 2 students in, what, 6, 7 months, was it? Yeah. So, you could imagine if you had a program with 8 students at the start, and then 6 months later there are only 4 students, then you could say the half-life is 6 months. That's how long to lose half. So just be careful. If you were 6 months later, how many would you have? So if you went 8 to 4 in 6 months, another 6 months you'd have 2, yeah, and then 6 months after that? 1. Because half-life is the time to lose half of what you presently have.
But isn't that just approximation?
Of course,
Well,
yeah.
that's why the decay rate reduces.
It depends on this, yeah. So are we clear what half-life is? Yeah. And this is very common in physics, chemistry and biology as well. So in biology even you have this notion called LD50. Just a little bit. Just a little bit. I know because you're in the physics class, but just a little bit, okay? So there's something in biology called LD50. So it's how much of a drug you have to give people so that you would kill half of them.
Half of people?
Yeah. So of course you do this with mice first. So, something like, what medication would you have at home? Paracetamol or something like this. Of course, if you take too much of it, that would be fatal. So the number usually used in biology is something called LD50, which is how much of the drug you would need so that if you gave it to 100 people, 50 of them would die. So it's quite normal in physics, chemistry and biology to have this notion of how long until you have half of something. Okay?
It's like an experiment of giving to 100 and then waiting.
Well, it'd be 100 mice, and then after mice, it'd be 100 dogs,
and
then monkeys. Never people, though.
Well, why do they plan
It's a good idea to know how much of a drug will kill someone. So, as a doctor, you don't give them too much, right?
That is so cool. To kill mice and dogs.
Yeah.
And monkeys.
You eat like chicken, don't you? So why is that not cruel?
But anyone be killed for something.
What?
It is to kill for you.
Yeah, kill for scientific
That's
research.
survival.
That's better than killing for your lunch, I think.
What's the point?
Your lunch benefits how many people? 1. Just you.
Yeah.
Scientific research benefits all of mankind. In fact, your lunch is more cruel than that. Logic 1, punish 0. Right. Now, half-life can be related to decay. So let's look at the formula for half-life and K, because they can be related. Okay, so if I replace the T here with the half-life time, then what will the N be here if I start with N0? N0 over 2. So this would be a half N0 equals N0 E K half-life time.
Why is that half N?
What I'm doing is I'm putting in the half-life time to try and find the formula for K. So I know when the time is the half-life time, I'll have exactly half of what I started with.
Do we need to cancel any zeros?
Now we need to cancel out zeros. And then how can I cancel the E? Log, oh sorry, I left out my minus here. So now I have log 2 to the minus 1 equals minus k t a half. So the minus 1 can come down, and then this minus can cancel this minus. So I get log 2 equals k t half-life. So now we have a formula for the k. The k is equal to log of 2 divided by the half-life. So if you know what the half-life is, you can know what the k is. And if you know what n0 is, then you can know what the n is. This k is given a name. Any guesses?
Decay constant.
Correct. It's called the decay constant. What's the unit?
1 over second.
Yeah, per second. Which one is what? What's per second? There's another unit for per second, which is what unit though?
Right.
Yeah. Okay. So decay constant hertz. Okay, so we need something else to do with this now. So to recap, we have two formulas in total. We have this one for the k, and this one here for the n. So formula 1 and formula 2. Okay? Now there's another thing we're looking at now. So at the beginning, let's imagine, for example, just as an example, there are 10 alpha particles. At the beginning, let's imagine there are 10 alpha particles being released from our uranium or whatever per minute. So after 1 minute, would you still have 10? No, you should have less coming out. Yeah? So we measure the decay by how much is released per second or per minute. So again, at the start, this is when the most is coming out, and then later it will be less. This is called the activity. Activity is a measurement of what's called counts per second. Literally, how much radiation is you're counting per second.
But isn't that not stable every second? Like, it just
No.
decreases?
No, it decreases. So like at the beginning, maybe there's 10 per second. Then an hour later, maybe there's 1 per second being released. It's like an ejection rate. You know. Anyway, so we'll put it down here. Activity. So the unit here is what we call number of counts per second. So just to be really clear, am I talking about how many alpha? How many beta? What exactly do I mean here? Well, in fact, what we count is how many isotopes we lose. So for my example, when I said 10 counts per second or per minute or whatever, that means I'm losing 10 uranium-233 isotopes per minute. Okay, so we count the loss. Do you know this annihilation? You know this word, annihilation? Or loss, destroyed. Yeah. Okay, so this is here, and this count here, in my example of uranium, is the number of uranium-238 isotopes lost, and then this here is of course per second. So it's clear enough. But another way of describing activity, that's one way of describing it. Yeah, we usually use just A. Activity is also the rate of change of n. So So you have two actually formulas for it. Yeah, but the second one now can be a bit more useful, because what is rate of change in mathematics? In maths, what's rate of change? The derivative. So another way we can look at it is activity is the time derivative of n. But what is n? The formula for n? n0 e to the minus kt. And what's the derivative of that? Minus k n0 e minus kt. But what is this piece here? It's n again, isn't it? So now you get a equals minus k n. Now, do we have a formula for k?
Yes.
Yeah. So if you know how much you have, you just multiply by the decay constant and you can know its activity. Often the minus is not included because we use, a bit like, remember, deceleration. Do you put a minus in deceleration? No, well, we don't usually, because the word deceleration already implies the minus. So, again, with activity, you don't worry about the plus or the minus. Okay, so now we have three formulas. Yeah, that was number 3. This was number 2. Okay, let me give you some examples now. Let me just check. So what I'm going to do is let me just give the example. It's whatever Arabic student uses this to keep the language in it here.
Okay.
No, you haven't lost your mind. Don't worry. U38 halfway. Oh wow, 4.5 billion years. Yeah. Yeah. Maybe we'll use something a little bit shorter. So, what about sodium-24 or carbon? Carbon-14 is 6,000 years.
12 hours.
Sodium-24. That's more realistic. 14.9 hours, is it? Okay, so you have 1 mole of sodium-24. What's that? Well, the thing about uranium-238 is half-life is 4.5 billion years. This is the reason why it is present in nature. Because its half-life is so huge, there's not been enough time for it to all decay away from the Earth. But like sodium-24, do you think that occurs in nature?
No.
No. Yeah, so 15 hours and then it's gone. So I think there's been enough time since the beginning of Earth that there's no sodium left. But uranium-238, there's still lots of it left that can be mined from the Earth. It hasn't all decayed away. Okay.
What can that be used for?
We'll look at nuclear power plants later for the uranium. Well, it doesn't really matter because you're not going to be able to buy it. You can't just walk into a shop. No, it is valuable. It is valuable. Yeah. It'd be per kilogram. It'd be quite expensive per kilogram. see. Price, supply, no, don't know, Joshua. I'd say probably more than you can afford. Okay. 1 mole of sodium 24.
$30. Yeah.
No, couldn't be $30. If it was only $30, I feel like I should buy some of it then. It's cheap. Alright, anyway, 1 mole of sodium 24, that's what we have. And also, the half-life is, what did we say, 14.9 hours. Okay, so question 1 is the mass at time 0. Question 2, well sorry, no, that's not 1. That can be question 2, mass at time 0. So number 1 is what is n0. Number 2 is what is the mass at the beginning, so that's m0. Number 3 is what is the activity at the what is the decay constant. Number 4 can be what is the activity at the beginning. 5, 6, mass at the beginning. What is A after 1 day? No, one more. When will it decay to 0.125 moles? So in other words, how long until we only have 0.125 moles left? So I'll give you a couple of minutes to use your formulas to get me those answers. Oh, you might want to, you probably want to know the molar mass of sodium as well. Let's have a look. Isotope. Yeah. Just take it as 24. So 1 mole. Oh, well, I'll give you the answer. 1 mole is 24 grams is 1 mole. I get the right way around? Yeah, 1 mole is 24 grams.
Can you go back to the discussion?
Yes. N is a count, it's a number, there's no unit. Think chemistry, put your brain in chemistry mode.
This is amazing because that chemistry.
What? You have not recovered? Oh, by the way, sorry, I forgot to tell you. I'm sure you can figure it out, so, what is the unit for activity? Can you look up? What's the unit here? Well, it counts per second, isn't it? So, yeah, but it's how many of a thing per second, so it's not quite per... If you want, you can just say the unit counts per second, but it's named after the person who discovered it. So, I'll just put on a side note here. I think you got it. Where's my pen gone? Pen, come back. Anyway, I'll just write here. B, first letter. E. C. Q. Very good. So 1 BQ is equal to 1 isotope per second. I have to fix the pen, I know. 1 destruction per second. 1 destruction per 1 second. A BQ. Okay, so back to down here. Huh? Again, for the third time, yes, it's math. What? It's destructions per second. So, for example, if I start shooting at birds and I kill them at a rate of 5 per second, then that's 5 destructions per second, so 5 BQ. Well, yes, everything's all right. Don't you worry. Okay, are we nearly finished this? Yeah? Okay, what is M0? Oh, hang on, let me fix my pen. Okay, what is M0 and N0? The first one. No, the first one.
6.02
Thank you, what does the Turner say again?
6.02 times 10 minus 20.
What number is that, Hanish? Yeah, you have 1 mole of sodium, which means you have an Avogadro number's worth of sodium. So this is how much sodium we have. What is the mass? 24 grams. So if I keep it in kilograms now, that would be 0.024 kilograms. Did you work out the K? The K is
1.319.
hang on, log 2 over 14.9 times 3,600. We usually do it per second, usually. So what number is that now?
1.319 times 10 power minus
1.319?
5.
Thank you. 1.10 to the minus 5. And the unit? Hertz. Okay. The activity, I won't worry about the minus. Is the K answer multiply what? The activity at the beginning. So just take this answer and multiply it by this answer, and what's the activity at the start? Whatever. Okay, whatever. 77 times 10 to the 18. And the unit? Yes. What is the activity after 1 day? Now, the thing is, you first have to work out how much you have after 1 day. So we have n equals m0 e to the power of minus k times t. And what does that come out as? Yeah? Are you sure? I really doubt that minus sign there. Positive 23, yeah? 1.97? Yeah.
That's right.
Right, so that's the n after 1 day. So how do you find the activity after 1 day? Yeah, so just multiply this by the k, please, and tell me what you get.
2.5 times 10 power 18.
Okay. The last part is something that should remind you of math class. We want to find the time so that we have this many moles. Now there's a little trick I want to show you. I find this trick very convenient in the exam, so watch carefully. We have n equals n0 e to the minus kt.
What are we looking
This is, listen, pay attention, teacher showing you trick time. If I multiply n by k, what do I get? Activity. So if I multiply both sides by k, what do I get on the left? Activity. And then here, activity at the beginning. But also, what is n? N is Avogadro's number. So if I n is the number of isotopes. So if I divide n by Avogadro's number, then what have I got?
Moles.
The number of moles. So I could divide by k and I get this, or I could divide by Avogadro's number and I get the number of moles. It is not. No, it's not. It's not. If I have 10 to the 100th isotopes, I would need to divide by Avogadro's number to know how many moles of isotope I have.
We're talking about
The what?
You just say divide by k.
Did I say divide by k? In my
all of us and this is
all of them are, yeah. In my head, I was picturing multiply as well. I'm sorry.
You know it's not.
And you're right, Todd, it really doesn't matter. Right, so if we divide by Avogadro's number, we have the number of moles. So you also have number of moles equals number of moles at the beginning, E minus KT. But of course, if you multiply now by molar mass, what do we get? The number of moles multiplied by molar mass. We get mass. Do you notice anything in common with these formulas? They're all the same thing, aren't they? The thing you want equals how much you have at the start times this E piece. So if I want to know how long until I have 0.125 moles, I can just use that instead of n or a or whatever. So we have 0.125 equals, how many moles are at the start? 1. E to the minus, and what's the K?
Or 1.29 and 10 to minus 5.
Yeah, and we're looking for the T here. So we have log, 1 is gone, and so that cancels the E and log here. So we have log 0.125 equals minus 1.29 times 10 to the minus 5t. So t would equal 1.29 times 10 to the minus 5, oh sorry, upside down, would equal log 0.125 over 1.29 times 10 to the minus 5. What's that, please? And give me the answer in hours. How many hours? 44.8 hours. Yep. Now watch this. Can I scroll down? At the beginning, how many moles of sodium 24 do I have? No, the minus is cancelled. It's time, it has to be positive. How many moles do I have at the beginning? 1. After, what is it, 14.9 hours, is it? No, the half-life. After 14.9 hours, how much do I have? 0.5. 0.5. After another 14.9 hours, how much do I have?
0.25.
After another 14.9 hours, how much do I have?
0.1.
So, it should be the same as 3 half-lives. What's that, 27, isn't it? 4, 8, 12, and 2 is 14. 44.7. Not too bad. Rounding error, yeah. In fact, the 44.7 is more accurate than the 44.8. The reason for the inaccuracy is with the K. We have to round the K off. Yeah. Yeah. To where? Yeah. All right. Can you go back down, Thomas? A 6-minute break? Why 6 minutes? Weirdo. But why 6 minutes? Who asks for a 6-minute break?
You're present.
I would actually, but I most prefer no break and finishing sooner. You agree? We all agree. Right, can I go down now, Tanish? Okay, you got that? Yeah. Okay, secondly, do you remember when we did the lesson on capacitors? What type of graph did we have for voltage for the capacitor when it's discharging? Yeah. But we don't usually plot this. What do we usually plot? We want a straight line, don't we? We want a straight line? Yes? So we don't plot voltage. What did we plot? Do you remember? Log was the voltage. So we can get a straight line. So if you look here, if I have n equals n0 e to the minus kt, if I put log on both sides, I get log n equals log n0 plus log e minus kt. So I get log n equals log n0 minus kt. So I get log n equals minus kt plus log n0. Okay, so what I'll do now is let y equal log n. and put on the x-axis t. So then this becomes y equals, this here, we call it the slope. So y equals mx, and this here will be the c. So in other words, if you draw this graph with time here and log n here, what type of graph would you get? Straight line, yeah. Going up or going down? Whoa. You're right, going down. Why going down? Tell me, come on. No. The n, what's n? The slope. Minus k. And what type of graph is a negative slope? This or this? No. And what's this point here on the y-axis? Log n0. And the slope here, what do we say that equals? Minus k. So in the exam, this could be a question where they give you the n, and then they ask you to draw a suitable graph. So we should calculate the log, yeah? No, just how to graph it. Let's look at an example. By the way, you can do the same thing with activity. So if you had activity equals activity 0 e to the minus kt, what should you put on the x-axis? Time. And what should you put on the y-axis? Log a. What will this point here be? Log a 0, and the slope? Minus k. So let's have a look at an example, something like you could get in the exam. So this is time, and this one here is this is time, and this is activity. And what's the unit for time? Seconds. Seconds. And the unit for activity? Activity? Yep. Okay, so let's say here at the beginning there are, let's say, 10 destructions per second. And then 10 seconds later there's 5. And then 20 seconds later there are 2.5 destructions per second. Now you can get 2.5 is fine, but you might say, how can 2.5 isotopes disappear per second? What we haven't really talked about is the decay is actually random. So not to worry about it, 2.5 is acceptable, but what 2.5 would mean is that there's a 50% chance, of a 50-50 between a 2 and a 3. We have this picture of this nice, smooth, exponential curve, but in reality, if you look really closely at it, it's kind of jagged. It's not actually smooth. So don't worry about the 2.5 here. And then 30, can you see what's happening here? What's the half-life? What's the half-life time? 10 seconds. So what should this one here be? It should be this one divided by 2. Okay. So, you know, in the physics exam, there's usually one question in section B which asks you to draw a graph on graph paper. So the possibilities are what? Part 1, mechanics. What is the graph they could ask you to draw on graph paper? Velocity time graph. Part 2, electricity. Voltage and current, or no? Yeah, which graph? What does that graph have? That is time and log voltage or time and log current. Yeah. Waves. There isn't really a graph, although there has been one example which we'll have a look at, but very, very unlikely. Then the next part, fields. Any graphs there? No, not really. And then materials. Any graph? No, but you might have something. You might have something to do with stress and strain.
Is there any energy graph?
Or energy graph. It's not so common though. Usually the energy graph is just a sketch. And then for atom, it's this here, the activity or the N. Okay.
The graph is usually spectral against time.
No, it could be N against time. And you have, not N. What are you supposed to do with your data? You shouldn't plot N. What should you plot? It's not time and N or time and activity. What is it? It's log. So what will happen in the exam is they'll give you this table and they'll say, number 1, part 1, extend the table. Number 2, graph the data. Number 3, what is the slope? Number 4, what is the intercept? Number 5, from your graph, estimate the half-life. This is typical. So I'll give you a minute, please, to draw this. You'll need your calculator to calculate the logs, okay? So I'll give you a couple of minutes to do this for me. Of course, in the exam, you will neatly do this on graph paper, right? Because you're just throwing away marks if you don't. Very close. No. The graph is not always, but nearly always linear. Very unusual for it not to be linear, although not impossible. So again? In fact, I think the normal thing to write in is log BQ. Say again?
No.
You drew the graph? Good. So once you have the graph drawn, I'd like you to get the slope and the intercept.
You want A0 or log A0?
No, once you have the slope and the intercept, have you done that for me?
Yeah.
I want you to use your slope to give me the K. And then,
What is slope is it?
yes, and then to give me the half-life. So once you have this graph, John, I want the slope and the intercept. Then I would like the K and the half-life. Yeah, the K is equal to minus the slope, is that right?
No. For the length.
Yeah.
40 and the second is negative.
Oh yeah, that's okay. Yeah, we'll go underneath the axis, yeah.
There are two variables. So,
Say again?
there are two variables.
Why are you talking about those two variables? You're giving your teacher a headache.
Sorry?
I want to see these graphs. No good. Doesn't even have numbers on the x-axis. Fine. Fine. See? Fine. Show me. Don't be shy. Show me. Yeah. Fine. Good. Finish? Okay. Don, soon, did you get the half-life yet? Yes, can I see your calculation? So what did you get for the slope? Did you draw in the triangle? I thought. Yeah, I want you to draw a triangle. Yeah, measure the two. It's okay, yeah, it's for today. Yeah. Mm-hmm. Yes? You need to use the formula that has the formula number 2.
Yeah, I do, but sometimes really access to find half-life.
Will they ask that? Yes. Because in my example, the numbers are clear from the table. This will not be the case in the exam.
So they usually draw the graph, they usually
What could they ask you? Yeah, they'll either ask you for the half-life or the activity at the beginning. But that means that they don't give you the time 0, which is kind of strange. So I don't think they'll do this. I think it's always going to be, what is the half-life? This is the most common question for this graph.
So because they half-life, you use the equation, not the...
You have to use the value, you have to use your slope to get the K, and then the equation to get the half-life from the K, equation number 2. Yes, for half-life. It is. It is exactly 10. Yes. Yes, because of my choice. No, it is exactly 10. No. Listen carefully to my words. It is exactly 10.
So after I found gauges and intercepts,
Did you, the K, get the K now, and then get the half-life of the K.
K is the graph is drawn what
It's minus the gradient. What?
once the graph is drawn what
Find the intersection one, and find the slope, and find the K, and find the half-life.
Do you want me before class to decide, alright, today, let's annoy him by doing this?
just wait below the
This is on a picture. Hey, Charles, Joshua here. Right, here's the plan. We'll both wear black t-shirts today, and you and I in maths, and I and I in physics. Right. So, when are your auditions for your boy band you're doing for Charles? Isn't that boy bands, they all wear the same colour t-shirt or something, isn't it? Who would be the lead singer though? Tanish is a member of the band, is he? But he's not in the uniform. Tanish, where's your black t-shirt? Oh, he's the lead singer, is he? Yeah. No, the half now, he looks more like the drummer.
I'm the drummer.
He's the drummer, yeah.
In real life.
And the name of the band, let's see.
you
Stephen plus 4, yeah. My musical talent would be quite limited. I'll be like shaking a tambourine or something, or at the end.
I bet you wouldn't be able to do that.
The triangle.
That's actually pretty hard.
It's just the triangle. I'll take it. I can have it what do you call it? The singing, isn't it? You know, this is when they pretend to sing.
In the case I got 9.9. I just did the good decimal places.
Well, yeah, not too heavy.
Well, let's have a look at it now. What? I'm going to draw it anyway because
This is for
he will be, he's probably worried right now. He's missing the class and he's thinking, well, at least I know Stephen has recorded the class.
What happened to Mohammed?
That's for you to discuss with him, it's not for me to say.
But he wrote his assignment.
He did all his assignments, did he?
He did the lab report, but he got -100. The penalty for the very late submission.
I never got a lab report.
And he was thinking, there is no point already, -90.
I don't know, there's always a point. Okay, so time and then log A. So we have 0, 10, 20, 30, 40, 50, and then here is log activity. I think you said, Tal, it goes, oops, it's gone wrong here. Oh, sorry, it's log 5. Oh, for goodness sake. I'm tired. Log 5. Log 2.5. Log 1.25. Log 0.625. Log, please look up this one here. Did you get that as well? Yeah. Okay, so we'll graph it now. Please, have mercy. It's very tired. Right, we want this, and we don't, that. no legend, X and Y. X-axis is time in seconds, and Y-axis is log activity in log BQ. Title, my graph. Okay, finished there. Right. Yeah.
Nice point.
Yeah.
GG.
That graph. Right, so insert trend line. Okay, so we have to get the slope, but I can see from looking at it, the slope looks like it's roughly 2.2 over 30, something like this. But the program can actually get it for me exactly, if I get the equation here. So the slope is minus 0.069. So the slope is minus 0.069. Okay? So that means the K is 0.069. Well, let me be a bit more accurate. 69315. Now, what's the formula that relates to K and the half-life?
K equals the log 2 over
K equals log 2 over
half-life.
half-life. So that means half-life equals log 2 over K. So log 2 divided by this number is 10. Because log 2 is 0.69. So I can see that is 10 times the size. So it's exactly 10. Yeah? What's wrong? Are you okay? Right, let me give you these questions.
So this graph is a 10 marks.
Yeah! See, the graph question is great in the exam because no matter how stupid you are, you have to find marks in it. Don't do that, please. Even though that's bullying, okay?
Usually when you don't look, you right.
Really?
See, that's the same.
Look, he's going to punch you in the face one of these days.
Can I have a paper?
Alright. Alright, please try these for 5 minutes and then we'll go.
And then we want to do it.
What do you do in 4 minutes?
What?
Fine, please do these for 4 minutes and then you can go.
I have an extra copy.
Just keep it, it's on the house.
I before when I was asking if I could use an app to solve it.
Yep, just make sure you reference that app, what you use. But yes, that's encouraged, that's absolutely fine.
The amount, the due next week, it will be.
It's not due on Monday, isn't it?
No, we have to get tomorrow. Or what you're talking about.
The math project is due on Monday.
Yeah.
Because if you remember, 2 weeks ago I said it was due in 2 weeks. And a month ago when I gave it to you I said it was due in a month. It's funny that, isn't it? Yeah. It does, doesn't it? And I even warned you about that as well. But, oh, that's a business to me.
On Friday, on extra month, will you be able to give us last advice?
Oh yeah, do you want to do something like that?
Yeah, just everyone can do something.
No, we have to be careful because the rule is like B301. So we can't have everybody coming for their project. So people could bring their project, but I don't want any lazy students just showing up that haven't done anything.
Yeah, that's what I meant.
Yeah,
Bring the project and give them
we can have we can see about that, yeah.
Yeah.
Friday, extra math. Yeah. But she's taught the program as well. She taught the science and engineering maths 2 years ago, so she knows what the program is. It's just this year she's teaching business.
The last topic.
Atoms, yes.
Oh, okay. No,
I prefer to teach the engineering maths, and she teaches the business maths. Maybe next year we'll swap again.
more heavy.
What is business math? Statistics all the way through. Okay.
Yeah, but you see, maybe I need a break next year from engineering maths. Look around you.
You're also right.
Oh, just do.
No, I accept this, yes.
So we do the question, read the topic.
When? Oh, you mean for physics?
Yeah.
Oh, you mean for the exam tomorrow? The deadline? No, wait, I mean the exam revision questions tomorrow.
Oh.
You want to have a look at, wait,
Look at the topic again.
yeah, so for tomorrow, Joshua is looking for a wave question, double slits, okay? Materials
I
question.
don't want to do it. Question everyone wants to go through the topic here.
Exactly. Like we teach, not really we teach, but like briefly.
I can do exam questions and explain as I go along.
No, it doesn't.
That doesn't work.
We did already
We do that.
Have you looked at the videos?
It's not the same thing. You can think about it.
Is there anyone who wants to do waves again? No.
Yeah.
Just don't do it.
Double
You know
slits.
waves?
Yeah.
You know the waves topic? But I have really nice question.
Just for what? Like three topics.
No, you think it's not too much?